we are slowly gathering. So while we are reaching the number of the people who are applied to attend, let's meet our host for today, our speaker Boris. So while we are waiting for all the people to gather, maybe Boris can tell us a little bit about himself and about his road to Symphony and what Symphony has brought him.
I can indeed. Thanks, Yana. Hi, hello everyone. My name is Boris Popov. I live and work in Novi Sad. I have been programming for a while now, probably ever since the dial-up, so a long time. And yes, I am that old. Maybe I don't look it. So yeah, here at Symphony, we have a lot of cool and interesting projects. We are primarily focused, of course, on modern technology stack. When it comes to backend, our primary stack is Java with Spring Boot, so also Node.js as well. Then on the front end, we're working with React applications and, of course, cloud-based solutions, distributed architecture. When it comes to deployments, we're using containerized application. We're typically orchestrating them on cloud, preferably AWS, of course. And when it comes to orchestrators, Kubernetes, AWS Fargate, those kind of things. And so when it comes to Symphony, Symphony has 5 hubs in Novi Sad, Belgrade, Niš, Sarajevo, and Skopje. So if you live in these cities or you're in the neighborhood, just give us a call. We would like to talk to you, of course, and we are always looking for a talent. So if you're up for it, we're ready to talk to you. That's my plug.
Thank you, Boris. So the number is rising. We have more than 100 people here. Maybe we can wait a couple of more seconds for the crowd to gather, and we can start. But yeah, so first I will give a little intro about myself. So my name is Jelena, and I am a community manager in front of the Symphonies Hub in Novi Sad. I want to thank you all for coming to this web meetup. Since we are all working from our homes, as you can see, Symphony colors around us, but we are really trying to stay safe and healthy, and we hope you do too. So Symphony has been in this work from home setup in a while now, but that really doesn't stop us from sharing our knowledge in this way and covering different topics. And we really have plenty of those. So I really wanted to say thank you for coming, and I hope you will enjoy this 1.5 hours with us. We will have a neat presentation and some awesome games and challenges for you. So while sharing the knowledge with you, we also care about you remembering stuff and using that knowledge in the future. So today, Boris will present some of really interesting problems that can be avoided, and you can overcome those problems by using Kafka. So after this presentation we will have today, we will have also a really cool quiz that will show us who remembered the most out of what Boris was saying. So stay tuned, listen carefully, and be quick so that you can win some really cool prizes. So other than that opportunity to win some really good stuff, we will also check your knowledge later after the meetup, when we will send you a mail with a small challenge or a task, if you will, for you to solve by using all the knowledge you acquired during this meetup. So if you would have any questions during the presentation, feel free to ask them in the Q&A section or in the chat. Boris will answer them later. So I will now hand the spotlight to Boris, and we can start with the meetup.
Thanks, Jelena. It's funny how you mentioned the interesting problems. And the problems are never interesting. It's annoying, I would say, mostly annoying, maybe challenging. But I don't know. I wouldn't call them interesting. Anyway.
I don't understand, so I will say interesting rather than confusing.
Okay, cool. I'll share my screen now, and hopefully you can see it shortly. Okay, so you should be able to see the presentation now. Okay, yeah, okay, we're good. And I'm going also to switch off my camera for now because of my internet speeds, of course, if I can manage to find it. Give me a second, or 5. I lost my Zoom window. Stop video, here it is. Okay. Can you still hear me?
Yes, all good.
Okay. Okay, I've lost my Zoom for whatever reason. But if you can hear me, that's fine. That's perfectly fine. So anyway, let's start. As I said, here in Symfony, we have been working on a microservice approach for a while now. It has been years that we've been working with the distributed systems and microservices. So there are some challenges that we face on every project, and it seems that we have to solve them all over and over again. So that's kind of why I chose Kafka as a topic for this meetup, because I think it can help us with a lot of challenges that we faced in a distributed world. So let's start with the typical example. Of course, this is when we talk about microservices, there are a lot of benefits. Autonomous teams, independent deliveries. We can scale on a service level. We can choose technology depending on the team, of course. There's a certain separation of concerns. There's a certain, there's less complexity, of course, on smaller levels. So we have some benefits when it comes to simplicity as well. So all in all, it seems like there's a lot of benefits to go with microservices. It doesn't fit every scenario, of course, but in most cases, when you have high loads, web applications, global applications, it's a safe bet that you're going to go with microservices. Now, one of the first fundamental things when we have to solve when we work with microservices is we have to enable them to be autonomous, and the only way we can do that is to make sure that each service holds its own data. So it has an ownership over its own data. This sounds like an easy enough challenge to do, but very soon we figure out that it's not a clean cut as we think. So we have a lot of these things. All of these services need to know something about customer, and typically what we do is we have some RPC calls, which are probably going to be some HTTP or gRPC if you're advanced, which is far from ideal, of course. 3 things about the HTTP is fundamentally problematic with HTTP is its synchronous nature, speed, and network reliability, of course. So pretty soon we see that these calls are costing us a lot of time, and it's not just get customers. Pretty soon we get into the situation that each service needs to know something about the other service. So customer wants to fetch orders and shipping and payment, and pretty soon every service is calling every other service, and we get into the really low performances. So in order to combat these performance issues, what we do is kind of cache aside thing. We would get a customer and put it in cache somewhere and not use it. And of course, as it is typical in distributed systems, we are solving one problem and we are introducing 3 other problems. So now we have to invalidate this cache. We have stale data, and When do we really want to invalidate it, and are we showing the wrong or right data and those kind of things? So it's getting a bit complex. Then on top of that, we're not just fetching entities. Like we don't only need to fetch a data model. We also need to orchestrate these things between themselves. So if a customer received an order, it needs to send an event to payment saying clear the payment for this order, and then payment needs to ping back saying yeah it's paid now. You can go to orders and those kind of things. So now we have we are exchanging data over these APIs, but we are also having these messages over the APIs. So pretty soon it looks something like this. It gets less and less autonomous. It gets pretty messy pretty quickly, of course. And over time, we get into the situation when we have really slow systems, unreliable systems. And if you think we had spaghettis in the monolith, now we have this, which is kind of distributed spaghettis. I don't know what it is. It's like spaghettis, but longer and slower, and it breaks easily. Does it make sense? Anyway, it's a mess. It's a mess, and pretty soon no one can release by themselves. Everyone is dependent on everyone else. The system is going nowhere at this point. And this is I've chosen this as a bad example. This example is like how to fail with microservices 101. Of course, we know how to do this better, and we know the way forward, of course, is some event-driven architecture, maybe some domain designs, domain-driven designs, those kind of things. So let's start with a clean slate now. But before we do that, I'd like to talk a little bit more about this data ownership thing. What we are doing here is we want to separate data model into our separate subdomains or bounded contexts or whatever you want to call them. Now, what we're really doing here is we're artificially separating the data. In real life, data looks something like this. So for some of these entities in the data model, it's perfectly valid. Stock is perfectly valid in orders, and it's perfectly valid in the shipping. But of course, we can't keep it in both. We need to have it. We need to have a single source of truth. And this is kind of one of the core challenges that we face. We need to be able to share it and not share it at the same time. And are we able to solve this? Are we able to work around this? Well, yes, probably. And for now, just keep this in mind. We'll get back to this one. But of course, since the presentation is about Kafka, it's spoiler alert, it's probably something to do with Kafka, right? Okay. Now let's start with the clean paper. Let's talk about event-driven architecture, DDD style, for instance. So in a data-driven design, we are going to work with the events through a message broker. Message broker can be, well, typically it's a pub sub kind of thing. It can be hub, bus, whatever you want to call it. Now, when we have an event coming in, let's say this is from a web server, we have an event which is saying create an order. In domain-driven world, this would be, we had a basket, and this basket is aggregated into one order. We are saving that order, saving that aggregate into our database. And only after we've saved it in our database, we're going to push an event to a message broker. This would be an integration event, right? So we've already persisted. This is an event that has already happened, and we're going to publish it to other interested parties. We're going to say order has been created. Okay. Now, and in this point, message broker is going to transmit this message to other interested parties. Now, at this point, we still have to solve orchestration, of course. Somehow we need to orchestrate these systems between themselves. And what we usually do is we're going to either leave it to them to be autonomously, to synchronize autonomously. That would be a choreography pattern, right? And we might introduce some kind of orchestrator that's going to do that for them. That's one thing we need to do. Another thing we need to do here is we need to be able to solve any kind of error that has happened in this case. So as I said, this is an event that has happened. The action has happened. The order has been created, and the user is already notified, or your order has been created. At this point, for instance, shipping service says we made a complete mess. We don't have this in stock. I don't know how we sold it. We need to be able to go back and inform order that this order needs to be canceled. So in that case, we're orchestrating another call which is saying cancel this order. We are canceling the order and we're sending an apology letter to the customer, whatever. This is all, yeah, and yeah, this is in DDD world. These are actions and corresponding compensating actions, right? That's all fine. We know how to do that. We know how to use Saga pattern. We know how to use the choreography or orchestrator. What we usually miss here is when it gets this message broker, people usually overlook the message delivery. How well it is delivering messages, right? So, for instance, if this message and of course in the network there are going to be network partitions. Some messages are not going to be received. It's just a fact of life. It's not a question of if, but it's a question of when it's going to break. And if for whatever reason we get into the situation that I've sent this message, this is like a fire and forget. I'm just creating an order, and I might care about at some point I might be concerned about compensating actions, but at this point it's just fire and forget. If this message to shipping does not arrive and shipping does not inform me that nothing has happened, that we don't have it in stock, I won't be able to do my compensating action. So this is, if message delivery fails, we get into a whole range of edge cases which we need to solve. Like, it's easy to solve those business cases. Like it's a finite number of cases that we need to solve with orchestration and with Saga patterns. But when it gets to messages failing, messages not being delivered, I'm not sure which one has broken, and it can be to the shipping, it can be to payment, it can be to customer. All of these messages can be received, can fail. There's a lot of cases to cover. And of course, we get into the situation, we need to write this into that ledger queue. We need to read it from that ledger queue. Is it too late to work, if my service is down, for instance, is it too late to read it after a minute or 5 hours? I don't know. So it's not ideal. It's a lot of work to do. Sorry. In addition to that, these things keep persisting. When we talk about bounded contexts and those data in between, we still have these get customer kind of things in order to get the information about the entities from other domain models. Now you could go through events all the way. So you could say everything is an event, like customer is created, that's an event. Customer has been updated, that's an event. Everything needs to go to message broker. You need to be subscribed to this message. You need to figure out how you're going to deal with this customer data. which again, with this kind of pub/sub system, it's really flawed. It gets into a lot of problematic cases, of course. And yeah, those cache asides are still there. We haven't solved anything about synchronizing data. That's the one. So yes, it's better. It's a step in the right direction. But can we do this better? And I think we can. The thing is, it's not that we're bad at programming. I think that actually technology is letting us down here. In this particular case, this message broker is letting us down. And that's why we get into a lot of trouble. So I'm not going to talk about orchestration. I'm not going to talk about the Saga pattern and those kind of things. I'm just going to focus on how do we make these messages reliable. And in addition to that, how do we solve this synchronizing data as well. Now, in addition to that, if there's let's say there's a service that's just late to a party that we've just started working on. How do we get it up to speed? Well, usually it's some kind of batch process here, like I'm going to fetch the data in some batch semi-automatic kind of thing, and then I'm going to put it in database. Again, not ideal. We're going to solve that as well. And in the end, when we're talking about data analytics, again, it's really risky to go through these events with the message broker. Usually, it's just another batch job. We have a lot of batch files created, transformed into a different schema, right? The data guys, they love their stars and snowflakes, and it's kind of manually put in the database. So so that's where we are. How we can do it better? That's the question. But yeah, another thing I would like to talk about this reliability when it comes to message broker. I would like to again stress out how bad this can get. So let's do some calculations, okay? I'm taking the AWS SNS as an example of pub/sub. It's not just AWS. I'm not having a go at AWS. It's any kind of pub/sub. So SNS currently has 99.9 uptime SLA. And with 99.9 uptime SLA monthly uptime, we can have 0.73 hours downtime. Now, let's say we have moderately medium-sized system which chews through 100,000 messages per hour. 100,000 messages per hour is not a lot. You could have a couple of thousand concurrent users, maybe 1,000 concurrent users making 100,000 messages in the message broker. So that would be 37K messages lost just for the downtime of the Amazon SNS. And while preparing for this presentation, I had a look at the latest SLA numbers just to be precise, and I've noticed something interesting here. So it says 99.9. And then they have some, they're covering for possibility that it can go lower. And specifically, this one is really interesting. If it goes down to 95% of the time, you still have to pay 75% of the price. So this looks like the way this SLA is worded, looks like they kind of expect to go down from 99.99. And let's take this 95% SLA and see what we get up to. So if it's 95% uptime monthly, we'll get into quite a lot of downtime. It will be a 36 hours downtime, and this medium-sized system is going to lose 3.6 million messages. Now, imagine systems like Netflix famously has, I think, a couple of million messages per second. And with this kind of SLA, yeah, well, you can do the math. It's just something that we need to take into account. And this is just lost messages by message broker. You still have to think about network partitions. You still need to think about your own services downtime as well. So it doesn't look good, that's for sure. Okay. Another thing I would like to point out as a problem here when it comes to this synchronizing data thing, for each of these services that we have, these are kind of integration points that we need to integrate with in order to have our data up to date. So we have a message broker, dead letter queue, maybe some batch processes. This is that cache that we're updating from time to time. We are pinging customers directly through API, and then we also have to expose our own API to the outside world. So a lot of integration points, a lot of complexity, just to keep our data up to date, synchronized. Okay, so that's those are the challenges basically. Network speed and reliability, data consistency and eventual consistency, service dependencies, distributed transactions, synchronization, and back pressure. Back pressure, I'll get to that a little bit later on. So how can Kafka help us solve these problems? Now, if you're new to Kafka, you're probably overwhelmed with the articles about Kafka. I know I was surely overwhelmed the first time I read about it. There's so many cases that people are using Kafka for completely different reasons, and when you start reading about it, it's not an easy subject to go through, right? So let's try and demystify it a little bit, okay? Kafka consists of topics, and when we strip down to the topic level, a topic is just a commit log. It's a commit log of append-only records, so records can only get to the end, and they are immutable, and a record is, we can call it a record, we can call it a message, we can call it an event. What it really is just a key value pair and the timestamp, sorry. Key value is just a byte array, okay? It's whatever you put into this byte array, Kafka doesn't really care. So that's all that is just a long commit log. Now, in order to get this commit log, to get a record into this commit log, we have producers. In order to read from this commit log, we have consumers. Now, one big difference from the pub/sub kind of thing, pub/sub, of course, is push. This is pull mechanism, which means these two consumers can read at their own pace. So consumer 1 is reading on offset Y. When the consumer reads this record, it's not going to go away. Records are persisted. So when consumer gets to that point Y, it goes along at its own steady pace and gets to the point Y. Record is still there. It's not lost. So this is also important thing. So records are append only, immutable, persisted. And that's kind of all that it is. Kind of. So yeah, I'm simplifying things a lot here. I'm skipping through a lot of things just to keep the message streamlined. But at this point, you just have to trust me that Kafka is distributed and fault tolerant. It has at least once message delivery, and actually in latest releases, they are working on exactly once message delivery as well. It has really high throughput, and it can achieve near network speeds of event processing. And yeah, behind the curtains, there's things like partitions, nodes, consumer groups, those kind of things. But I'm just going to skip over them right now. And really important things when it comes to architectural things that I'm going to show later on. The records are immutable. I'm saying it for a third time already. Multiple consumers pooling at their own pace, and the records are persisted. Now the records can be persisted. I think the default is 7 days. It can be less, it can be more, and it can be forever. So you can persist records forever in Kafka. Let's now compare that to the typical pub/sub. In typical pub/sub, what we saw is we have publishers, one publisher and multiple subscribers. When we publish a certain message, it's going to be broadcast as a push to all of these subscribers. So this is a point in time. All these subscribers need to react at that point in time to the incoming message. Now, if there's any kind of network partition or anything like that, maybe the subscriber 3 is offline, maybe it's down for whatever reason. That's presented with this error being broken down. This message did not receive subscriber 3. It has to go to a dead letter queue, and then at some point when subscriber 3 gets back online, it needs to read it from dead letter queue. Okay, so this is, and okay, typically pub/sub is going to retry like 3 times or whatever. And for instance, AWS SNS doesn't even have, by default, doesn't even have dead letter queue setup. So if you leave it to default, the messages are lost. Let's talk a little bit about back pressure now. As I said, each of these subscribers need to react at this point in time. So if there's a lot of, if a publisher gets a lot of messages in, and suppose these subscribers can't really keep up for whatever reason, maybe we didn't auto-scale them properly, maybe we can't auto-scale them, we've ran out of resources or whatever. It's just going to, the messages are just going to be coming in at higher pace than we can process them. And this is kind of a back pressure that I was talking about. We can't really deal with this. We're going to lose a lot of messages this way. Now let's compare that to a Kafka topic. Kafka topic works a bit differently, of course, as I already said. We have once a producer creates a record, that event state persists in a fault-tolerant way, and it's as I said, for now you have to trust me that it's fault-tolerant and that it's distributed. When we put a record, we know for a fact when we have received a message back from Kafka saying record is stored, we know for a fact that this record is going to be stored in a fault-tolerant way. Consumers now don't have to react on this particular record right now. Consumer 1 is really lagging behind, for instance, and if there's a network partition in this particular case, or this consumer goes down, it's not a problem. Consumer Kafka knows that consumer 1 has stopped reading it at this particular offset. When consumer 1 gets back up to speed, gets back online, it's just going to start continue reading from this particular point in time. And of course, this helps us with this kind of complex setup. We don't need dead letter queue because we already have this as a queue, and we can deal with the back pressure in an easier way. We don't have to react to a message straight away, which are quite important things, quite important benefits, I would say. Let's have a look at some code now. So producers and consumers, oops, sorry. Producers and consumers are, we have an abstraction over producers and consumers in Java world. It's a producer API and consumer API. How do I get this out of here? Go away, bye. It's just a part of your Java application, okay? So it can be, it's just a dependency in your Gradle or Maven build. In this case, it's Maven. I have this Kafka clients. This is all I have to add. And now I can write producers and consumers. So as an example, let's have a look at this one. So first we do some bootstrapping. We are saying what our servers are. As I said, Kafka doesn't care about the type, but we care about the type. So we need to provide a serializer and deserializer in this case. And then we have this Kafka producer. In this case, we're going to put a string and a string in a key and a value pair in this particular topic. So not really much to it. It's just a producer abstraction, which says send producer record. That's it, we're done. It's that easy to produce messages in Java. An example of the consumer. Again, some bootstrappings going on, serializer, deserializer. I'm going to skip over this consumer group. It doesn't really matter right now. Actually, it matters a whole lot of deal, but not really right now. And this is my abstraction Kafka consumer. I'm just going to put it in while true loop, and I'm going to consume records. Now, in this case, I'm polling 200 records at the same time to optimize things a little bit. And yeah, it's done. I'm consuming messages. Now, you might be wondering how do I deal with this offset thing? You can leave it to leave it to auto, for instance, which is perfectly fine. You don't really care about the offset yourself. It's between Kafka and the client, the consumer API itself. Another thing is scaling this thing. Of course, you can scale. It's a part of your application, so as many instances as you do, as you create for your own Java application, you'll get that many instances of this consumer. If you're wondering how Kafka does it, I already mentioned we have just one topic and now I have multiple consumers reading. It's handled. It's handled. I'm skipping that part. But for now, you need to know that it does work. You can scale. You can scale horizontally. You can work in parallel, and you can get a high throughput when reading messages. Okay. So we've talked about the possibility to use Kafka as a message broker in event-driven architecture when we use it to broadcast events. Now, what if I do something like this? What if I enforce a certain schema on my topic? So for instance, I'm enforcing this topic to have this customer info schema. And customer info is just JSON, which has ID, first name, last name, contact email. Now, this is what the Kafka record is going to look like. Value of the Kafka record is going to look like. Now, when you look at this record, it doesn't really look like a message anymore. It looks mostly like some record that you would put in the database. Now, the question is, can we take this record, not put it in database, but put it in Kafka topic? And not just this record, but actually take all the records that we have about customers and put it in Kafka topic. And in this case, I've already mentioned that records can be persisted forever. So let's say we've created a topic which is called customers. Its records are persisted forever, and I'm filling it with the records about the customer. What I have created looks like it's a topic, it's a string, but it actually looks also like a table in some sense. So can we use this topic as a single source of truth for customers, for instance? One of the things which are going to be challenging is because this is evolving fact. This customer can be changed. So I can get updates to the first name or the last name. Maybe I'm married, or whatever. That's fine because Kafka has something called log compaction. So if I put the record with the same key and I switch on the log compaction, Kafka is going to go through my topic and delete the records which have the same key. So it's going to be only the latest key is going to be left in the topic. So essentially we have created something that looks like a single source of truth for a customer. Now let's see how we can use it as a single source of truth. Suppose my customer service is creating these records in the topic as a source of truth, as I called it, and the other services are not directly reading it with the API from the customer anymore. They are reading it from this topic. So whatever customer puts in this topic, this is now the truth. They are getting updated from this topic, and they can store it in their own materialized views. So this materialized view is created to be optimal for reads, for instance. It can be cache, can be database, can be anything. Now this setup looks like we're getting somewhere with this setup, but we have to write a lot of these producers and consumers. We have to write a producer here. We have to write consumer here, here, and here. And then we have to go through our repository, create a repository for all of these materialized views and those kind of things. So it looks like there's a lot of work to do still. Can we make this easier? Of course. Let's go there. Now let's talk a little bit about Kafka Connect. By the way, it's really strange that I can't see your faces right now because the things I'm talking about, like topic, the source of truth, is probably some heads are turning right now. But anyway, it is what it is. Let's continue. Kafka Connect is, if ever there was a silver bullet kind of solution when it comes to integration of the data, Kafka Connect is probably one of the best in that field. So what Kafka Connect does is it scalably and reliably integrates your data between any data source into any destination database. It's a standalone application. It's not a part of the Kafka cluster. It's you can host it as a standalone service. It can be a single instance. It can be a cluster, but it's standalone. What it has inside it is connectors. Now we have source connectors and sink connectors. Source connectors are going to read the data from a database or any source. It's going to push that data into Kafka Topics, and then sink connectors are going to read those topics, or any other topics for that matter, and store it into the destination database. Now, one cool thing about Kafka Connect is it supports a whole range of connectors, and the community is really, really large, and connectors are really loads and loads of connectors. I'm just going to mention a few here. So if you're working with JDBC driver, you have source and sink connectors for anything that can connect with JDBC. CDC, I'll talk a little bit more later on. Elasticsearch, Sync, Spark, HDFS, Cassandra, Postgres, anything in AWS, like S3, Kinesis, SQS, Lambda, Dynamo, Azure, GCP, MQTT, and then also the social networks as well, like Twitter, GitHub. It can read from RSS feeds. It can read from a lot of things. So basically, what it is a way to integrate any kind of data with a zero code into your Kafka topics, and then later on sync it into wherever you want. So let's have a look at this example one more time. We don't have to write those producers and consumers. We can do it in a better way. We can do it like this. So I'm not going to write a producer here. What I'm going to do is write into the database. Let's say this is a Postgre database. Then I'm just going to hook a JDBC source connector to my database. And then this JDBC connector is going to automatically push the records into the topic. On this consumer side, I'm not going to write any consumers. I'm just going to use JDBC sync. This JDBC sync is going to automatically fill my materialized views. And again, we kind of solved data sync problem with zero code here. This is something that kind of looks like CQRS, you would think. All of these materialized views, these are optimized for reads, right? This one can be Redis, this one can be Postgre materialized views, this one can be Cassandra, whatever this service needs, you can have it as the data source. It's automatically synced, and this automatic sync is near real-time eventual consistency. Okay, so yeah, I think this alone is really powerful thing, and Kafka Connect is a really powerful thing. There are cases where people use Kafka specifically just to sync data between different databases. Another cool example for Kafka Connect would be this. So for instance, you have some legacy system and you're tired of working with this legacy system through APIs. Well, you don't have to work through APIs. You can use a CDC source. CDC source is a Kafka connector which reads change data capture. And change data capture is most of modern databases support it. It's effectively a transaction log of the changes, of the mutations that happen in your database. So whatever changes happen to this legacy DB, CDC source connector is going to pick it and put it in the Kafka topics. And you can do with this data whatever you want. You can synchronize it with your own service. You can do some streams app. We'll get to that in a minute. You can put it in your data lake, whatever you want to do. Let's have a look at one more example of the integrations. So, as I said, any kind of data coming in to any kind of target going out. So, for instance, we can have our services creating topics through JDBC connector. Legacy systems can be synced through CDC connector. Third-party systems can be connected through HTTP source connector. We have HTTP source connector as well. And all this data is then synced into Spark RDD, for instance, I put here, and then HDFS or whatever you have on this side. So this looks like, when it comes to data analytics and data warehouses, this looks like, when we talk about ETL, it looks like we have solved E and L in this case. We have extracted the data and we have loaded the data. Can we also solve T with Kafka? And now this is different to a normal ETL. Normal ETL would be the kind of batch thing, semi-automatic batch thing. Now here we are talking about real-time ETL. And can we solve ETL real time? Can we solve the T part, transformation part with Kafka? Again, yes, of course. It's called Streams API. Streams API is a Kafka component. Again, it can be a part of your application. It's a dependency in your Maven and Gradle builds. Stream A stream is basically an unbounded sequence of structured data. So this can be events, called them events or facts. It began way back when the application started, and it's never going to end unless there's zombie apocalypse. But that's the only edge case. Otherwise, it's never going to end. Now, a K-stream is an abstraction over this stream. A K-stream is a Java class. We created using a K-stream builder, and we can work. Well, I have a code example, so we'll see how K-stream works. A table, on the other hand, is we also created from Kafka Topics, but it's a collection of evolving facts, and these evolving facts are. Think of it as the customer example. So this is a customer record is going to evolve over time. So we might change the address of the customer. We might change the first name or whatever. We can take these evolving facts, and this is going to be a fixed set. It's not running forever. And we can take this fixed set of records and put it into a K table. A K table is then going to be stored in your memory. And of course, the question is this a single point of failure with in-memory K table? No, of course it isn't. You can scale it to as much instances as you want. Now, why would we create these streams? I can give you a couple of examples. A stream is, as I said, a never-ending process. We get new and new events coming into the stream. We want to be able to deal with them in real time. We want to be able to transform them in real time. We can take one K stream, then in real time do some transformations on these records. And with these mutated records, we can create another stream. We can create a new stream. And then in this new stream, we can create a new Kafka topic. Then behind this new Kafka topic can be any kind of consumer that wants to read this data changed. So a real life example would be, maybe this topic came from a third party service. It doesn't really comply to our schema. We are going to transform it here like a kind of anti-corruption layer, right? We're going to transform it into our own schema, create a new stream, create a new topic from this stream, and then consumers are going to read it in our own schema the way they understand it. Similarly, there's a change when we talk about data warehouses. Schema for data warehouse is completely different than your own schemas. So we can do this kind of thing as well. We can take a stream of the data coming in, we can transform it, put it into different schema and load it into a data lake. Or we can also do some kind of aggregations, and we can do it. We can do aggregations based on a certain point of time. So we can do these are called windowing. We can aggregate the data in a single day, or we can aggregate the data per month, per hour, whatever we want to do, and then take this kind of data, aggregate it, put it in the data warehouse, and do analysis on it in near real time, as I said. In this example down here, we can take a stream, put it in K-stream, and then we can also take a topic and put it in table. And then we can do operations like joining. The reason for joining stream and table would be to enrich the data in some way. For instance, maybe this is orders are coming in, and as orders are coming in, we've also materialized customer view. we are adding address to a record, for instance. So we now have a new stream, which is going to be a new topic that has an order and the customer's address. And for instance, shipping service can use it later on for their purposes. So there's a lot more scenarios than these. These are just a couple of ones, couple, 2, 3, how many I had. Examples. Now, this is a streams example. Again, we have to do some bootstrapping at the beginning. As we had, similarly as we had with the producer and consumer, we have to serialize and deserialize the data. That's what these SERDs are for. It's called SERDs, serialize, deserialize. And data record is our model. Now, this is the stream builder that I was talking about. We're taking a topic. We're using a builder to build a new stream. This stream is going to be typed with the data record, right? It's a key value pair of string data record. Now, when I put this in stream, this looks, to any Java developer, this looks fairly similar to Java streams. And indeed, it's made to look like Java streams. So we can do on these records, we can do things like map, reduce, filter, those kind of things. Now, as a result of my changes to the stream, I'm creating a new stream, which is counts. I don't know what have we done here. We've counted something, and I'm putting it into a new stream. Now with this counts, I'm doing some additional work. I'm doing some grouping. I'm doing some reducing. I'm putting it again into the stream, and so on and so on. So to any Java developer, this looks kind of familiar, right? And it's made to look intentionally like that. Yeah, one more thing about the streams and the code that I've shown you. This kind of thing is as I said, the stream never ends. The stream is continuously going. Well, so is this operation. This operation is continuous. It's going on and on and on and on, and it's never going to end, right? That's kind of the difference between stream and the table. Okay. Now, I think we've covered everything we wanted to cover about Kafka. I hope you have a better understanding what Kafka is right now. I've mentioned how it can solve problems with messages being lost and problems with data sync. Now let's ask the same question again. What is Kafka? Well, yeah, in the core, Kafka is that commit log that we saw. But with all these things on top of it, like source connectors, sync connectors, streams, producers, consumers, it's really a platform. It's really a platform that can do a lot of cool and interesting things. One thing that should be in this picture, and I haven't talked about, is KSQL. I'm not going to cover it here, but basically it does exactly the same thing as Streams API do, but for non-Java people, let's say for data analysts or anyone else. There's a link in the appendix. With all these things, let's try and zoom out a little bit and make this event architecture once more with Kafka in the middle. Now, first thing I'm going to add is the producers and consumers. These producers and consumers are going to do things like publishing events, like item has been added to basket or order has been created, and consuming those events, thus subscribing to those events. So these are kind of producers and consumers are going to be like publisher, subscriber in the event-driven architecture. Now these things are going to create a stream of events. Now this stream of events is Kafka Topics. We can keep this short-lived, or let's say 7 days is probably fine to be able to read and go through these records. And of course, any one of these subscribers can consume these events and work with them in a manner that I've described. So a pull mechanism, no back pressure, no messages lost, those kind of things. Then we can also put source and sync connectors. Now I've explained what source and sync connectors do. Let's put them in here. These are going to produce topics, which I call here entities, but these are facts. These are facts, evolving facts topics, right? And these ones we want to keep forever. These ones we're going to switch on the compaction log, and we're going to keep forever. Now with the streams in the middle, we can work with these stream of events and stream of entities or tables of entities or whatever we have. We can work with them in yeah, I forgot about this one. We can also hook in legacy, third party, anything else. It's going to end up in here as topic. Now with the Streams API in real time, we're going to deal with this data. We're going to deal with this incoming stream of events. We're going to process the data. We're going to take the processed data and sync it back to services, sync it to data warehouse, do whatever we need to do with this processed data. It looks something like this. So these are the changes we have done. So when I said technology is letting us down with PubSub, this looks much better, I would say. Now, finally, we can give this architecture a name. Of course, this is what it's referred to as a streaming architecture. The streaming architecture is a system which is able to safely and reliably ingest a lot of data with high throughput, react to that data in a fault-tolerant manner in real time, and produce some kind of results. So, is there anything else I wanted to say? I don't know. That's pretty much it, I think. Hopefully you'll find this interesting. As a conclusion, I would like to say I've just covered a couple of interesting topics when it comes to Kafka, but I've barely just scratched the surface. There's a lot more that Kafka has to offer, and I haven't even begun to cover topics like strong ordering. Kafka has strong ordering, which can help us with some concurrency problems. I haven't mentioned message queuing. I haven't mentioned any kind of parallel work. There's a lot more to Kafka than just this presentation. So as a conclusion, I would like to share with you this quote, and I'll give you a minute. Now this quote is, you probably guessed it. It's Bruce Lee quote. Actually, it's not Bruce Lee, it's from his master, but never mind. Now it's a bit of a stretch, but bear with me. Why did I put it here? Like water is shapeless, and like the water being able to take any shape, if you put it in a cup or in a bottle or whatever, you can take the same principles with Kafka. If you take Kafka and use it as a message queue, it will become a message queue. If you take a Kafka and put it as a PubSub, it will become a PubSub. If you use it as a store, it will become a store. So in the end, if Bruce Lee's message was be water, my friend, my message would be, actually I haven't really thought it through. My message would be no, use Kafka, yeah, maybe. So my message would be use Kafka, my friend.
Thank you, Boris.
Yeah, that's amazing. Thank you. You do have questions in the chat section and the Q&A section, so you can go through them now.
Yeah, I can, but I've kind of lost. All I see is my screen presenting. I'm going to stop sharing right now and see if I can see anything else.
So
Um,
we can read them out, or you can read them out if it's easier for you.
yeah. Oh, okay. Forgotten. Yeah, there is a data retention, of course, as I mentioned. It's one of the cool things about Kafka, being able to store the records forever. That's as an example. There's a big debate about should we keep data in Kafka and should we keep it as a single source of truth. There are examples of people already doing it. So, for instance, New York Times famously stores all of their issues from 1980, 1890 something to this day in Kafka. So it is possible, and people are using it.
Okay, the next questions are in the Q&A section. You can see it, Boris.
Mm-hmm.
There are 6 of them.
Okay. So if we end up with a scenario where the message is consumed by a consumer, but for some reason the message is dropped for shipping, how do we identify such incidents and how to build robust systems? If the message is consumed by a customer, but for some reason the message is dropped by shipping. Now, if it is dropped by shipping, there are 2 possible scenarios. Either this is a business case and shipping is saying, I don't accept this message. There's a business exception, and in this case, shipping needs to be able to send an event saying cancel this. If the problem is technical nature, like there's a network partition or the shipping service is down for whatever reason, it will get up eventually and it will read that message. So those are 2 different cases. I hope that answers your questions. I haven't covered anything about exception handling. Sorry about that, Yelena Lazarevich. I haven't covered anything about exception handling. I dropped it from the presentation. So it's a topic for itself, but there is a way to do it, and there are a lot of cool things on the internet. You can read up on that one. But yeah, you can even use Kafka as a log aggregator, of course, and those kind of things. What if message is corrupt or will break up? Well, it would be as with any kind of message broker. If you put something wrong in the message, you're going to break your system. It's up to you. You need to take care of your types. Sorry, but there's no silver bullet for that one. If it's not too complicated to explain, how is the consistency of offset for customer of topic achieved? How is the consistency of the offset for a customer of a topic achieved? Okay, so there's a couple of things we can do. We can configure this. When a consumer reads the message from Kafka, Kafka can reply straight away saying, I got the message, and then you go on with your work. Or there's also a mechanism that you wait for Kafka to write this to a disk. So it's configuration. You can wait for a Kafka to write this into a disk in a safe place, and then when it says it's written, then you go on with your work. So that's one of the ways we keep consistency of the offset. However, we still have a problem. We can get into the problem like you saw in, I'm using a consumer, I'm polling 200 records. If I straight away say to Kafka, reset my offset to next 200, and I have an exception in my application, I'm going to lose that data. So you can consume those 200 records, be absolutely sure that you've consumed them and worked with those 200 records, and only then inform Kafka to reset your offset. That would be most fault tolerant, I would say. Does that answer the question? I hope so. This is a long one, Alexander. Can I leave this one for later? It's really long.
Yeah, sure.
It has a lot of questions.
We
Sorry,
can,
Alexander.
yeah, we can also contact Alexander if you want to via email.
Sure.
Yeah.
Sure. When would you recommend using JDBC connectors? When would you publish directly? That's one thing I haven't really mentioned in my talk. I didn't want to complicate things. The way I described it in diagram kind of conforms to domain-driven design principles. So first, I'm writing from a consumer into the database, and then when it's persisted in the database, at this point, I'm triggering an integration, kind of integration event through the JDBC connector, right? It can be the other way around, of course. It can be, I could use publisher to publish directly to a Kafka topic, and that's probably most fault tolerant. If I first write an event into the Kafka topic, and then take a sync connector on the customer as well, on the customer database, it can work as well. So yeah, you can use publisher. Maybe it's even better to use publisher. But then you would use a sync connector from Kafka topics, because the topic itself is the source of truth. It's not customer's database, right? Thanks, Albin, for nice words, kind words. Yes, true, Yelena, I agree. RabbitMQ, I haven't really talked about Kafka as a message queue. I've only covered in this kind of event broadcast kind of way. But you can use Kafka as a message queue as well. It works differently. Kafka as a queue it can be used kind of like a queue, but it's not a queue. The difference is probably it scales better than RabbitMQ. RabbitMQ supposedly have some problems when you try to host it as a cluster. I haven't tried it, so I'm not going to knock it. But yeah, I've been using RabbitMQ as well, so it's fine. But I've only used it as a single instance, so not really. I can't really compare. And yes, another thing is when you use Kafka as a message queue, there's it's a topic for itself. I need to explain how partitions works and how customer groups work. Maybe it's RabbitMQ is easier to work with. If you just need to slap something together, RabbitMQ is probably easier to work with.
Okay, does that
yes? Sorry, just two more questions.
Okay.
On consuming topics and using this data combined, is it a good idea to use streams? Yes, but again, it depends on the scenario. If it's something you need to work in real time, like real time transformations, those kind of things, and put it in, because the result of streams API is always another stream. So you take some streams as an input, your result is always another stream, because this is an ongoing process. You're transforming these records on fly and creating another stream, thus creating another topic. So in those kind of scenarios, yes, it is a good idea to use streams. Horizontal and vertical. Yeah, I've as I said, I've completely skipped the part about Kafka as a distributed system. You can read up on it. There's some links in the appendixes in this presentation as well. Kafka is a distributed system. Minimum viable number of nodes for production is 3. You can go crazy, you can go to 100, you can go to 200 nodes. So I think probably these big guys, I think Netflix uses clusters with 200 nodes or something like that, and clusters in plural. So you can scale it. You can scale it horizontally, and it scales really, really well. And I think that's it for the questions.
You do have 2 more questions, I think, in the chat section.
Mm-hmm. When would you recommend using JDBC connector? When would you publish directly? I've already kind of answered that one in the Q&A section. Can you use Kafka Connect with custom serializer? Yes. I haven't mentioned Avro at all. So yes, Kafka does work with Avro. Thanks, Mihailo, for reminding me. Kafka does work with Avro, and subscriber, the producer and consumer APIs do work with Avro, and Streams API also works with Avro. So there's specific Avro SERDES. And it's a preferred way. I would say it's a preferred way to go with Avro. What backend languages environments can Kafka be used with? Yeah, I focused this presentation on Java, but of course there's a lot more. There's a lot more clients. You have clients for any kind of mainstream language. You have .NET clients, you have Node clients, you have Python clients. So you can use it with anything. I'm not really sure that you have something similar to the Streams API other than KSQL, but KSQL itself is really powerful and really easy to work with. So maybe that's a good match. Thanks, Yelena. That's it, I think.
Yes, that's it, I think, with the questions. And if somebody has more, just write them down. And Alexander, we will get you via email because it seems like you two could discuss this topic a little bit more thorough. So Boris will contact you with the answer, just so you know. Okay, Jelena, are we waiting for more questions or should we tune in for more? You are muted.
We should definitely move on to our quiz. So I will just share it. Okay, you guys just stay with us for a couple more minutes. We have amazing prizes, which Jelena already mentioned. I was supposed to be your co-host, but due to technical issues, I'm here for the quiz now. So a couple more minutes. We are glad to have you again. And we will now explain the rules of the quiz, which are pretty simple. So just go to kahoot.it, or if you have a Kahoot app already downloaded, you can use that one and type in this code. We already have our first participants here. Yes, so just be careful and write your name, your full name with the city you're from. Yeah, that's
for those who are already signed in, it's okay. But for the rest, please write your full names and maybe the initials of your cities, just so you know who you are.
Where you're from. So that's super important.
Yeah.
Okay, so we'll just wait for all of you to apply.
Oh, whoever wants to play. Whoever listens to the presentation carefully will have a big chance to win some amazing prizes.
Yeah.
Okay, we already have 31.
We hope you're confident about it and that you remember lots of things.
I would sign up, but you know, I would sign up for the prize, but I know the answer is not fair.
We could just guess. We would win.
Yes. Okay, 49.
Not bad.
Yeah, maybe, oh, I wanted to say wait till 50, but we have more. Wow, thanks guys.
Yeah, let's just give them some time.
Maybe 60.
Yeah.
But if we go about 60, we will wait for 70. Okay, 3 more players. Come on, 2 more players.
2 more players and we can start.
60 will we wait for? Oh.
Still rising.
I wanted to, but
we can't stop now.
yeah.
Okay, I think this number is here to stay.
If anybody has any problems with connecting, just write us in the chat. I think that's it, 62. Okay, 62 of you.
Okay, so let's start with the quiz. So you can answer these questions on your devices, which you're made the account on. So we will start with the first question. 3, 2, 1. So the first one is Kafka a push or pull mechanism?
Follow the colors and give your answer.
So let's have some music.
Yes. And more.
Come on. Be careful, you have the limited amount of seconds here. So, okay, most of you got it right. So good start, right?
27, is it more? Not really most, but who's first? Darian.
Darian is the fastest one who got it right.
Martin and Dusan. Okay.
Yes. So let's move on to the second question. What type is stored in the topics record? This
is fast.
Fast.
They know this. Okay.
Woo! Good work. Let's see who got it fastest.
Darian,
going strong still, but you know it's a close one. Let's go to the third one. What's the maximum retention period for a record of Kafka topic?
Oh, this is fast.
This is the easy one.
I guess. The last 4 people are struggling.
Yeah. Yeah.
Definitely.
Definitely the easy one. Boris, cut you some slack.
It gets easier.
Yeah.
Darian's still leading, but this doesn't mean anything.
Yeah.
Not that I'm not rooting, but
good work. Let's go to the next one. What's the name of the Java wrapper around Steams in Steam API?
Well, they really did pay attention.
Super smart people here. I would be this one waiting for the end. 43 correct answers. Great job, people. So K-stream, if that's how it's pronounced. Woo!
Oh, Miroslav.
Oh, how the tables have turned. Good work, guys. Let's go to the next one. How do we deploy producer API and consumer API?
Milan Markovic says, it says time up even if I submit the answer. Do you submit in these 20 seconds that you should? Maybe there's a bug.
I guess this was the tough one. Only 28 of correct ones. Kudos to those who did it correctly.
It could be a connection issue, Milan. I'm just talking with Milan here because he's typing and I'm answering.
We are not able to wait for him, but I hope he will figure it out. So the next question, how do we deploy Kafka Connect?
This is also a tougher one.
Yeah, I believe it is.
Time's up.
Ooh,
Oh, this was a tough.
This was the toughest one yet.
Remember, I got this right.
Yeah, that's true. So yeah, we deploy Kafka Connect as a separate service or cluster. Let's see who did it the fastest.
Milos, Vladimir, and Srđan, top 3. Just so you know, the top 3 places get prizes, so don't be pumped if you're not first.
Let's go to the next one. What Kafka connector types do we use? Couple more seconds. Ooh, nice result.
Table Sarab. Oh, Milos isn't.
Great work. And the next one.
Last question, right?
Are Kafka records mutable or immutable?
The last one, right?
Yeah, I believe so.
Oh, this was
Okay, great result. I think this is the question with the best result yet.
Yeah, let's
Okay,
just
so let's see who are the winners. So Srđan Pepić got the 3rd place, Vladimir the 2nd. Dagadam.
Milos first. Congratulations, guys. You can just write in the chat again if you're the first 3. Although Milos already, I think, identified himself. But the 2nd and 3rd place, you can write in the chat just to make sure.
Just make sure we get to the right people. So thank you all for participating. Let me just shush this music from the Kahoot.
Thank you, guys. It was lovely hosting this meetup. We hope you had fun and you learned something. It was productive. Okay, Srđan Pepić. Forgot to append the NS. Okay. Thank you very much. We will contact you with the task that gets after the meetup and with the materials for the meetup. Somebody asked if it's recorded. It is. You will get it all via email. And also, what else?
And you will also get the whole presentation that we prepared for you and presented today. So don't worry. If you didn't catch some of the details Boris told us about, you will have that in one place, all neat and great in the presentation. So once again, thank you all for attending, and yeah, hope we will meet again on in some other event. Thank you.
Thank you.